Hello and welcome to our first video on preparative chromatography. This video will try to help you in learning what is preparative chromatography used for, what are the basic parameters, and how do we optimize a preparative chromatographic separation so that we have the most yield and performance of our separation we would like to achieve. So what you see here is the basic starting point of a separation. On this side, we have a mixture of triangles and of circles. And now we would like to have a system which can discriminate between the triangles and the circles. And for that, we have something which is called a chromatographic system. So the most important part of a chromatographic system is a column. And in this column, we have the magic of the chromatographic system, which is the stationary phase. And our goal and our task is it now to design a stationary phase which will have attracting forces to one of these parameters here. Let's call it, or let's use the triangles for that. So we are designing something into the stationary phase which has attracting forces for the triangle. So while this mixture of triangles and circles is passing through the chromatographic column, the triangles will be returned because they fit to the stationary phase. The circles are not fitting to the stationary phase and they will flow faster through our column. At the outlet of our column, we have then two distinctive populations of particles. And in our system, we call that peaks, because what we do here is we have a detection system, which is typically a UV detector. And this UV detector cannot discriminate between the two different particles, but it can give us a quantitative expression of how much UV light is reflected on the system. So when we start here, we have the mixture. And to make our chromatographic system complete, we need something here which pumps the mobile phase through the system. So here we need a pump. And we need something where we introduce our mixture to be separated. So with that, we have nearly a complete chromatographic system. The only thing which is still missing, because we are working in preparative chromatography, is our goal is it to separate these here quantitatively, and we would like to have it collected in the end. So in contrast to analytical chromatography, we are really interested in what is coming out here to be separated, isolated, and further processed. So what we see at the end of our chromatographic system is a chromatogram. And a chromatogram typically looks like this. What you see is the time, or it's the milliliter of solvent which is passed through the system. And here you have the UV intensity. Typically what we see is a component which is not retained in our chromatographic system comes out of the column as the first peak. It's typically called T0 or column dead time. And then we have our chromatogram, our peak, which we would like to collect. And this peak we would like to collect has a retention time, which is the middle or is the maximum of the peak height. And we call that T1, the retention time of our column, which is the maximum of the UV signal. To compare now the retention time of different columns of different substances to be separated, we introduce something which is called K'. And K' is defined as the retention time of our peak minus the column dead time divided by the column dead time. With this K', the retention factor, our advantage is that regardless of the dimension of our chromatographic column, we can really have a dimensionless number, which gives us a number for how long a substance is retained in our chromatographic system. One very important point of our chromatographic peak is how broad is it? If you imagine that we would like to collect the whole peak, so because everything which is in here is of value for us, we start to collect, let's say here, where the first material is coming out of the column, and we stop to collect here. So this time between the starting of the collection and when we finish the collection, that is what is of interest to us. And now imagine we inject the same amount, but our answer, our chromatogram, looks different. So in the one hand side, it looks like this, a little bit broad, and on a different chromatographic system, we have something, same amount injected, which looks like this. So we start to collect here and we stop collecting here. And now we just say, okay, this is a time span of 10 minutes. And our chromatographic system is delivering the buffer solution with a flow rate of 100 milliliter per minute. So this will give, in the first case, a total volume of 1 liter of fraction, which we have further to process. On the other side, this chromatogram with a much narrower peak, which should be higher than and more concentrated, has a collection time of only 3 minutes. Again, 100 milliliter per minute of flow rate gives only 300 milliliters of fraction volume. And if you see now that we do that with very large columns and you have a difference of threefold the volume which is collected, you can imagine how important it is to have small peaks, to have very concentrated fractions. So how is a fraction and the narrowness of a peak now determined? So for that, what we have to introduce is the peak width at half the height. This is the total height, and here we are at 50%. And from this parameter, we calculate something which is called the peak number. N is the peak number, and N is something which comes from distillation. It's a little bit theoretical points. The higher the N number, the number of plates in a chromatogram, the more narrow a peak is. So we calculate that, the number of plates, by this simple formula, 5.54 times T1 divided by the peak half width square. So the higher this number, the more efficient your chromatographic system is. And you see, the smaller the peak width, the higher this peak number. So how do we manage to have a system, a chromatographic peak, which has a small peak width and a high efficiency? And the magic for that lies in the chromatographic bead. And that is the next point we will have a look to.